And welcome to 90s level internet today. So I am actively fighting with the iPad to get things to work on the screen, so we'll see how it goes. The reason the internet's being grumpy is the Amazon servers crashed, and because Amazon crashed, which is on like all the internet servers, everything is going chugga chugga chugga. So welcome to the 90s. We will survive. So this is what we're going to start with today. When we're given a function rule, if we divide it by the factor, so if we're given something like x minus c, let me zoom it in so it's not quite so tiny because it is argumentatively small. There we go. If we divide it by the linear factor, whatever we have as a remainder, so like when we did it in long division, that very, very, very bottom piece, our r of x, that is the exact same thing as if I substituted in the root. So when we have these linear factors, which are typically written as something like x minus c, we could think of that as having a root 0 x-intercept at c. And sometimes, instead of actually just substituting it in to have it spit out a value, we can run it through synthetic division. I mean, you could do long division, but that's so much longer even then. And whatever we have as a remainder is the exact same value as f of that root. So what we're going to do first is we're going to take this function and we are going to divide it by x minus 3, this f of x, and we want to divide it. And you absolutely could do this with long division. Totally fine, 100% will work. Unpleasant though. Whenever we have a linear factor, meaning I don't have any x squareds, I don't have anything other than just a factor, x minus 3, could be 2x plus 1, any number of things. We can use synthetic division, which is so much faster. The only time we really have to do long division is if we don't have a linear factor. If I had like x squared plus 2, because that one I wouldn't even want to factor into linear factors because that would not have real roots. If we have something like that, we will need to use our long division. But if we have a linear factor, we can use synthetic division. So we're going to remember how to do that in this step as well. When we have a linear factor, if we were doing long division, we would take the whole factor out in front and our whole polynomial underneath. When we're doing synthetic, all I want is my root, my 0, my solution. What is the root for x minus 3? 3. So when we set up our synthetic division, this 3 is going to go in the top left. Some people write the synthetic division symbol like this. Some people do it kind of like an upside down division. I genuinely do not care how you do it. I have a tendency to just do it this way because I'm lazy. The 3 is the piece we're going in. Instead of writing out my whole polynomial here, I'm going to put my coefficients. One thing that's super duper important to remember is we have to include every single term. So I will need for my x cubes, I'll need for x squareds, I'll need for x, and I need my constant. I should have one more term than the degree. So since this is degree 3, I need 4 coefficients in my synthetic division. And it's always going to go from biggest to smallest. So I'm going to start with my x cubed, which has a coefficient of 1. Then I'm going to put my coefficient for my x squareds, minus 4. Then I need my coefficient for my x's. How many x's do we have here? 0. We cannot skip any terms. Even if we don't have any, we still got to put a 0 there. And then we have our minus 5. So whenever we have a degree 3 polynomial, I will need to have 1, 2, 3, 4 coefficients. If we had a degree 4 polynomial, I would need 5 coefficients. If we had a degree 5 polynomial, I need 6 coefficients. It's always going to have one more than our degree. So this is kind of our base setup for synthetic division. We're going to skip a line, draw a line, really. This is the space where we're going to have work, and this is where our answer is going to be, down here. Our first term, every single time with synthetic, just drops it like it's hot. One drop down. First term always false. For synthetic division, we're going to take the bottom times the left and put it under. So we're going to have our 1 times the box on the left, 1 times our 3, and put it under here. So 1 times 3 gives me 3, and I'm going to put a 3 underneath that negative 4. So 3 goes here. The other major difference between synthetic division and long division. Long division subtracts, synthetic division adds. So now we're going to do negative 4 plus 3. Which is going to give us a negative 1. And then we get to go around again. Bottom times the left, put it under. So negative 1 times 3, put it under. Negative 1 times 3 gives us negative 3. And then we add. 0 plus negative 3. Negative 3. Bottom times the left and put it under. So negative 3 times 3 and put it under. It's going to give us a negative 9. And then we're going to add negative 5 plus negative 9. Negative 14. This last term, every single time, no matter what, this last term is the remainder. So we could write this as our r of x, exactly like how we had it for our long division, is negative 14. Absolutely valid. That is what we have as the remainder. It is at the very bottom. That is also the value of f of c. So if I was to take and substitute into my function my 3 that we divided by, as in 3 cubed minus 4 times 3 squared minus 5, we would get exactly negative 14. It is also the value of the function evaluated at that number. So if we have a remainder, that's exactly what it would be. So sometimes this is also called synthetic substitution because it's just like doing synthetic division. But it gives us our substitution answer. So our remainder is also the function evaluated here. These right here are going to be the coefficients of what would be at the top when we divide it. So like how this was cubes and we divided out an x, this one's going to start with a squared. Or you can go the other way and go constant x, x squared. Just like this one was our constant x, x squared, x cubed. It's always going to go down 1 degree down here. So I could find all the same pieces that we did on Friday, where we have our 1x squared minus 1x minus 3. That would exactly be our quotient, our q of x. So we can use synthetic division to help us divide. We can use synthetic division to help us substitute. Either way faster than doing long division. Because this would have taken 4 cycles of long division to get this answer. Ew. So that remainder theorem helps us do some substitution stuff. It lets us kind of simplify that process. And we're going to do another one of these. We're actually going to use the same function but a different factor. And do another substitution just so we can practice finding the function evaluated at. So questions on this one? Because we're going to use that same function, but this time what we're going to divide by is x plus 2. So it's the same f of x, so our coefficients for our synthetic division are going to be exactly the same. So if we set this up, we're going to have our 1 minus 4, 0, and minus 5. What is our root that we're going to divide by? Negative 2. Coming from this piece up here. We want to figure out our function evaluated at negative 2. We're going to find f of negative 2. That's what we care about. And yeah, we could type it in the calculator, but if this was a gigantic polynomial, it's easier sometimes to do this than to just straight up type things in. So first term always drops. Our first term will always drop straight down. So then we're going to take bottom times the left and put it under. 1 times negative 2 is negative 2. And then we add negative 4 plus negative 2. Gives us a negative 6. Oh, so funny. Bottom times the left and put it under. Negative 6 times negative 2 gives us a positive 12. 0 plus 12 gives us 12. Bottom times the left and put it under. 12 times negative 2 gives us negative 24. And then when we add negative 5 plus negative 24, we get negative 29. And what that tells us is that our f of negative 2, our function evaluated at negative 2, is going to be exactly negative 29. So it gives us our function evaluated at the root. I could find my quotient, that is my remainder. I have lots of options I can get from this function. Okay. What that means and is helpful for us is there's a specific remainder that's really, really important. And it's one we saw a lot in Algebra 2 when we were working with synthetic division. In fact, it's why we use synthetic division for a lot of things. And that theorem is the factor theorem, meaning if my function evaluated at a certain point exactly equals 0, then it's a factor of my polynomial. So if we take a root, zoom this in just so it's not quite so far out. There we go. If we take a root and divide it out and we get a remainder of 0, then we know that that factor is a true factor. If we get a remainder of anything other than 0, it is not a factor of the polynomial. So if our remainder is 0, then that's a root, or our whole thing is a factor. If the remainder is anything other than 0, that is the function evaluated at that c value, but it's not necessarily a root. So what we're going to do is very much like we have been doing. We're going to take a polynomial. We're going to find our c value. We're going to do some division. We're going to find our quotient and our remainder. And we're going to see if that factor is, in fact, a factor of the polynomial or if it's just some random statement. So this is how we're going to be getting those questions. We're going to find the quotient and remainder if f of x is divided by p of x. So what we're really going to see is x minus 2 a factor of 2x cubed minus 3x squared plus 4x minus 5? Is x minus 2 a factor of it? Because that guy's not really something we want to and or would like to factor at all. And in this case, it's actually not factorable by hand. So we want to see if this does divide out of that nicely. Could do long division. Don't want to, but I could. So I'd rather set this up with our synthetic division, which means I need to know my root for this statement here. What is the root for x minus 2? 2. You can take your x minus 2, set it equal to 0. You can just think of our x minus c, whatever it is, however we need to do it. So setting this up as our long division, or synthetic division, excuse me, I'm going to put my 2 here, and then need all my coefficients, making sure we don't skip any. So I've got my 2x cubed minus 3x squared plus 4x's minus 5. I have a degree 3, and I wound up with 1, 2, 3, 4 coefficients. So I made sure I didn't skip any. I should always have one more coefficient than my degree. Every time. If you do not have one more coefficient than your degree, you're missing one. You have to have that many. So when we do this the synthetic division, excuse me, same process. Our first term is still going to drop. So we're going to have a 2 down here. Bottom times the left, put it under. 2 times 2 gives us 4. And then we're going to add negative 3 plus 4, which gives us a 1. I'm going to make that darker. That feels very pale from over here. Bottom times the left and put it under. So we're going to have our 1 times 2 giving us a 2. And then we add 4 plus 2 gives us 6. One more cycle of it. 6 times 2 gives us 12. And negative 5 plus 12 gives us 7. This last term is always our remainder. So this is our R of x. Every single time. So is x minus 2 a factor of this polynomial? No, because this is not 0. If this is 0, and only if this is 0, is that a factor? So our R of x, what we get, our remainder is 7. If we did long division, and we got that number up on top, our Q of x, it would have exactly these coefficients. This would be our constant, this is our x, this is our x squared. It's always going to go down 1 degree. So this is an x cubed, and it starts with an x squared. So my 2x squared plus 1x plus 6 would exactly be that Q of x that we were working with on Friday. That quotient, that number on top. And I could do this again, just like how we had that polynomial kind of algorithm for how we could find, like, do a check, where we have our Q of x times our P of x plus R of x equals F of x. It does the exact same thing. This is just a lot less physical work than long division, because this one would take 4 rounds of long division. Ew. Synthetic division is significantly faster. The only downside to synthetic division, it only works with linear factors. With long division, I can use anything. I could use something like x squared plus 2, and I could divide by that. Whereas x squared plus 2, we can't really divide down into linear factors. Like, it doesn't factor well. So if we have a non-linear, so if we have a quadratic that we're dividing by, that's when we're going to need to use long division. If we have a linear factor, synthetic all the way, baby. So much faster. So much faster. We're going to practice this a couple of times. Questions on this one? Okay. Here's our next one. We're going to see if P of x is a factor of this polynomial. And I'm going to tell you, this polynomial, we need to be very, very careful when we are filling in our synthetic division. What is our root we're dividing by here? 4. So that's going to go over here. Synthetic division, we use our root. Long division, we use the whole factor. Synthetic division, we only use coefficients. So what are we going to put as we go across our coefficients? Yes. 3 for my x to the 5th, and then I have 0x to the 4ths, 0x to the 3rd, 6x squareds, 0 x's, and then 15. The most common mistake we get, and this is why I've said it several times, we're going to have one more coefficient than our degree. Our degree here is 5. That means I have to have 1, 2, 3, 4, 5, 6 coefficients in my synthetic division. Every single time. I cannot skip a 0, or my answer won't be just a little wrong. It will be so far wrong you won't be able to move forward with things. Like, it throws everything way off. It's not a little off, it goes way off real fast. So it is really, really, really important that we have the correct coefficients for our synthetic division. After that, our process is exactly the same. And I know there's several of you working faster and ahead of me. Your numbers are going to get very, very big. That doesn't mean you are wrong. They are very, very, very big. This one is kind of obnoxious with the numbers, which is why we wouldn't necessarily want to substitute this into a calculator, because we're going to look at this and go, I swear that's wrong. We're not, but it looks wrong. First term is going to drop. What's going to go into here? 12. And then 0 plus 12 is going to give us 12. Bottom times the left and put it under. So now we're going to have my 12 times my 4, which is a 48. And that's plus 0, so it's still going to be a 48. And then we're going to have another big jump. Because 48 times 4 is 192. And then we're going to add 6 to it. So 198. Not 594. Unless I'm wrong. I could be. There we go. And so we should get 792. Which means our very last set, 3,168 plus 15. 3,183. And it looks like we did it wrong. This also gives us a nice way to kind of check and make sure that things didn't go wonky without us going, oh no, I subbed it in the calculator. So, big numbers. So then, is this a factor of this? No, no, no. Only if this is 0 is that a factor. That's my remainder. That's my R of x. So I can write this as my polynomial division. My R of x is that 3,183. I could write my quotient, my Q of x, the number we got when we divided. And these are our coefficients. And again, you can either start from this end and go constant, x, x squared, x cubed, x to the 4th. Absolutely works. Or I can say it was an x to the 5th. So that means this guy's x to the 4th, and then it comes downwards. Either way, whichever works better for your brain, do it that way. But our Q of x, the number that's on top for, if we did this with long division, we'd have 3x to the 4th, and 12x cubed, and 48x squared, and 198x, and 792. Woo! So we have our division, we have our remainder. We know this is not a factor. Not a factor, absolutely not. We're going to do one more like this. No questions on this one. This is the longest one for today for sure. Because we can do this with any linear factor, whether we have a whole number or not. We could wind up sometimes with a factor that looks like this, x minus 1/2. We could have something that looks like 2x minus 1, which would also have a root at x minus 1/2. So we've got to be really, really careful, but we can absolutely do it. So we know that the root we're looking at here is this 1/2. Our x minus 1/2, that's what we're wanting to divide by. So when we set up our polynomial here for our synthetic division, our 1/2 is what we put up here. And then I need all my coefficients. So I'm going to have my 4x to the 4th. And then, what? 0. And then 1. So degree 4 means I need 5 coefficients. It's a really good way to stop and spot check. Please make sure you do. It is so important that you have the right coefficients. It is so important. Please, 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 please stop and look. Can you get a sense of something I've had to take a lot of points off for absolutely no silly reason? Please stop and check. Oh, fun. So, first term falls, 4. Bottom times the left, put it under. 4 times 1/2 gives us 2. 0 plus 2 gives us a 2. Bottom times the left, put it under. 2 times 1/2, 1. Negative 5 plus 1 gives us a negative 4. Negative 4 times 1/2 gives us a negative 2. 0 plus negative 2 is negative 2. And our 1/2 times negative 2 gives us a negative 1. And what's our remainder? 0. So is x minus 1/2 a factor? Yes. Bless you. Our r of x equals 0 means x minus 1/2 is a factor. Or our root, 1/2 is a root of this polynomial. So the x minus 1/2 is a factor, or 1/2 is a root. Either way, we know that. And then something that we're going to wind up using this for is if I divide that x minus 1/2 out, what we're going to be left with, our q of x, the number on top, is going to be our 4x cubed plus 2x squared minus 4x minus 2. If I took this times that plus this, we get that. That remember with our solving, or like our check algorithm, q of x times p of x plus r of x. This times this, now then added, is exactly that. If I wrote and multiplied this guy times that guy, I would get exactly that. These two things multiply together to make that. So this is actually a step we're going to use later in this chapter when we're trying to take a polynomial like this and break it all the way down into factored form. We're going to have to use some of this division when we get polynomials that don't factor nicely, like cubics and quartics and quintics. So 3rd, 4th, 5th, higher degrees. So we're going to use this for helping us factor big things. Questions on this bit? We have 2 more problems we're going to do today. Okay. Because we're going to look at those ones like we did on Friday that had the k in there, where we had to find k and it was like in a weird spot in a coefficient, like this. There we go. So we saw one like this on Friday, where we were given a polynomial and then we were given a point and asked to find k. So we substituted it in. This one, we're given our polynomial, and we're told that x plus 2 is a factor. So we're asked to figure out what k would be so that x plus 2 is a factor. Meaning, we want this root, whatever root we have there, to have a remainder of 0. If it's a factor, it has a remainder of 0. So our root here, what is the root for x plus 2? Negative 2. Meaning if I substituted that in and we looked at f of negative 2, it would be 0. So you could absolutely work it that direction. Substitute in negative 2 for x, set f of negative 2 as 0. Substitute it in just the way we did on Friday. I'm going to show you kind of a different way to do this. Absolutely works. We'll get you to the exact same answer. If we just have 1k in here, you can also do it using synthetic division. If you have more than 1k, like, we're going to substitute. It's just easier that way. But if I set this up as a synthetic division, because that's another option, I like to give you guys as many options as I can. You don't have to do it this way. You can substitute it, set it equal to 0, and find k. Absolutely valid. But if I set it up as synthetic, what we know is I know my x cubed has 1. My x squared has minus 3. My x has a minus k. And my constant is a 12. I have a third degree, so I have 4 coefficients, so I have all my pieces. I can kind of work this from either direction to kind of logic my way into what k needs to be. Because I know if x plus 2 is a factor by that remainder theorem we were just working with, my remainder has to be 0. Has to be. I also know I can start this just like regular synthetic division. First term drops. Bottom times the left, put it under. 1 times negative 2 is negative 2. Negative 3 plus negative 2 gives me a negative 5. Yes. Negative 5 times negative 2 gives me a positive 10. I can't add though right here. But I can kind of work from the right side because, well, I don't know what this needs to be. I do know what this needs to be. 12 plus what's going to give me 0? Negative 12. Negative 12. So I know that spot needs to be a negative 12. So this guy needs to be negative 12. Well, if this spot's negative 12, what needs to be right down there? 6, because 6 times negative 2 would give you negative 12. So I can kind of work from both directions to get where we need to be. So this needs to be a 6. So what that lets me know is that negative k plus 10 needs to equal 6. So what is our k going to be? 4. If we minus 10 from both sides, we get minus k equals minus 4. So our k is going to be 4. So if k is 4, then x plus 2 is a factor. So you can do it with synthetic division. If you have more than 1k, you can, but it is unpleasant. So we're going to do one more problem. It's going to be kind of icky looking. Breathe. This is our last one for today. And this has a whole lot of k's in it. Go. So we know that f of x equals kx cubed plus x squared plus k squared x plus 3k squared plus 11. Ugh. And we're asked to find k if x plus 2 is a factor. So this sentence that x plus 2 is a factor tells me a couple of things. What is the root we're looking at? Negative 2. What is our remainder or our value of f of negative 2? 0. F of negative 2 has to be 0. That's what it means for it to be a factor. Our remainder's got to be 0. That's that remainder theorem. So again, you could set this up as synthetic division. It is not pleasant to have both k and k squared in several places. Ew. So I'm going to do this the way we did on Friday, where I substitute some stuff in, because ew. If we substitute in, I know my f of x is going to be 0 if I substitute negative 2 in for every single x. So this is going to give me k times negative 2 cubed plus negative 2 squared plus k squared times negative 2 plus 3k squared plus 11. So substituting my negative 2 in for x, and then my f of negative 2 I know is going to be 0 if this is a factor. Bless you. We are down to one variable here. There's only k's left. Everything else is gone. So we're going to go ahead and simplify this as much as we can. So we know we're going to have our 0 equals negative 2 cubed times k gives us negative 8k. Negative 2 squared gives us a positive 4. Negative 2 times k squared gives us minus 2k squared. And the others didn't have any x's. 3k squared plus 11. Again, I've got things I can combine together. I can rewrite this in a slightly different form because I've got my minus 2k squared plus 3k squared. That's going to give us 1k squared. Got minus 8k plus 15. So combining some like terms together. Is that a factor? Mm-hmm. We can factor this. I mean, you can solve this in any number of ways, but the easiest way is probably going to be to factor this thing. So I could rewrite this in its factored form as my k minus 5, k minus 3. Because we know a pair of numbers that multiplies to be 15 and has to be negative 8, negative 5, and negative 3. So what are my solutions for k? 5 and 3. So if k equals 5, then x plus 2 is a factor. Or if k equals 3, x plus 2 is a factor. There's more than one option here. It happens every now and then. So you can either do these with synthetic division. You can do these with substitution. You can do these like on Friday when we got a point, and you can substitute them in that way too. So there's lots of different ways we can approach these. Okay? So a couple of really important theorems that we had here today. Questions on this one. Okay. So I'm going to put up our homework page. I've whited out a couple of dates simply because the internet's in a mood. Everything pulled up like last year's dates. There we go. 24th, November 7th. There we go. So here's the question numbers for homework 4-2. Remember, PSAT is on Thursday. We're going to have our quiz on Friday, and then our chapter test is November 7th. I will have for you guys, maybe tomorrow, but maybe not until Wednesday, I will have a review for quiz 7 since I'm not going to see you the day before, so that we have a little extra practice on that. No, you don't have to do it. It's not going to be like, I'll give you points if you do it, but I'm not going to penalize you if you don't. Just as a tool to study since we're not going to meet face-to-face on the day before the quiz.